In the first temperature video, we saw how placing a balloon in negative 196 degrees Celsius liquid nitrogen drastically reduced its size because the air particles were moving more slowly at the lower temperature and not exerting as much pressure on the interior surface of the balloon. We developed an understanding of temperature being related to the average velocity of gas particles. This begs us to consider, if we kept cooling the balloon to an even colder temperature, would the air particles move even more slowly? And would we eventually reach a temperature where the particles would no longer move, a coldest possible temperature? This coldest possible temperature, where all atomic motion ceases, does exist and is called absolute zero. We can't actually perform that experiment, but we can do something almost as useful. This apparatus is called a constant volume bulb. It contains air sealed in and uses pressure as a mechanism to indirectly measure temperature. We can change the temperature of the gas in the bulb and read off the corresponding change in absolute pressure. We will be able to crudely estimate the value of absolute zero from this data. Let's start taking data points with the constant volume bulb. We will place the bulb in substances where we already know the temperature in Celsius, temperature references, which will eliminate the need to use thermometers to make measurements. We first place the bulb in boiling water. Give it time to reach 100 degrees Celsius, and note that we can read off a pressure of 121 kilopascals. We next place the bulb in ice water with a lot of ice. Allow it to reach a temperature near 0 degrees Celsius and read off a pressure of 96.5 kilopascals. Note that it is a lower pressure, as expected. The gas particles inside of the bulb are not moving as fast and generating as much pressure at this lower temperature. Let's look at these 2 points on a graph. Assuming a linear relation between pressure and temperature, like the ideal gas law, we would expect an additional data point to fall on a line connecting these first 2 points. Lastly, we place the bulb in liquid nitrogen, which boils at negative 196 degrees Celsius. We allow the gas in the bulb to reach negative 196 degrees Celsius and read off a pressure of 33.5 kilopascals. Again, a lower pressure is obtained, as expected. We add the data point for liquid nitrogen to our graph. Note that it pretty much fits the same trend as the first 2 points. We see a steady increase in pressure as we increase temperature. Pressure is proportional to temperature. Let's explore this concept in a peer instruction question. Can you use this graph to estimate a value for absolute zero? The value of temperature where the pressure is zero because the particles are no longer moving. Which of the following is a reasonable estimate for absolute zero? Please record your vote on a piece of paper and explain your reasoning. Your instructor will now stop the video. If we draw a line as best we can through our 3 data points, we can see that it hits the x-axis where pressure would be zero at a value of approximately negative 300 degrees Celsius. This is the coldest possible temperature, absolute zero, where all atomic motion ceases. The actual known value is negative 273.15 degrees Celsius, as our method isn't particularly accurate. Physicists have created a special temperature called the Kelvin scale to make use of this principle. The Kelvin scale begins at absolute zero, and its degrees are the same size as the Celsius scale. Thus, there is a simple offset between the 2 systems. The Kelvin temperature is simply the Celsius temperature plus 273 degrees. So a difference between 2 temperatures is the same in the 2 systems. Often in astronomy, temperatures are large enough that this offset can be ignored. Note that although outer space has a very low temperature, it isn't as cold as absolute zero. You will learn about the cosmic background radiation in this course, the heat left over from the Big Bang. It can be observed to determine the temperature of space to be 2.7 Kelvin, 2.7 degrees over absolute zero, or about negative 270 degrees Celsius. More teaching materials can be found on the web at astro.unl.edu.